In this video, we're going to look at exponential and logarithmic equations. We'll look at 4 types altogether, 2 types of exponentials and 2 types of logs. In each case, there'll be an easier version where we're going to use the one-to-one property. I'll show you what that is in a second. And then there'll be a little bit harder version where we have to use kind of more the general property of logs to solve them. So starting off with the exponentials, like bases or one-to-one property of exponentials. So basically what this is saying here is if I have, like, for instance, 5 to the third equals 5 to the x, it's not really a mystery what x is. It's got to be 3, right? Because if 5 to the third equals 5 to the x has to be 3. So that's the one-to-one property. And so if I can get an equation, manipulate it so that it has a common base, b to the x equals b to the y, the only way that's going to be true is when x equals y. So let me show you what that looks like in practice. Pardon. Down here for this first one, let me rewrite it a little bit bigger. First thing you want to do is, isolate the exponential piece, as we do pretty much in all equations, is isolate it as much as possible. So I'll divide both sides by 7. Those reduce, and I have 3 to the n equals 81. And then this is asking what power do I raise 3 to get 81? With that one it would be a 4, right? So in terms of the one-to-one property, it's because 3 to the n, 81 can be written as 3 to the 4th. And so the n has to be 4. For this next one, seems like there's kind of a 5 situation happening there. So 5 to the x equals 1 over, instead of 125, let's call that 5 to the third. It's not quite one-to-one yet because this is 1 over 5. But remember from our properties of exponents, when we have a negative x or when we have an exponent in the denominator, I can write it to the numerator and change the sign to negative. Usually we go the other direction, but in this case it's handy to rewrite it with the negative. So 5 to the negative third, same as 1 over 5 cubed. X would then have to be negative 3. This one, if we had to solve it with logs, which we'll do in the next round, would really kind of be a drag. But because I have 9 raised to this exponent, 27 raised to that exponent, I could write the 9 and the 27 as base 3. So that would look like 3, not cubed, 3 squared is the same thing as 9, and then the tiny little 3x minus 1, I'll write here a little bigger so you can now see it hopefully. 27 would be 3 cubed, and that's raised to x minus 5. So now that I have 3 raised to something equals 3 raised to something else, I can set those exponents equal and solve from there. So I'll distribute as I rewrite this. 2 times 3 would be 6x, 2 times minus 1, so minus 2. 3 times x would be 3x, 3 times minus 5 would be minus 15. And then solving, I'll bring the 3x over to the side, so minusing from both sides, I would get 3x. Adding the negative 2 to that side, and I get negative 13. Divide both sides by 3, and x equals negative 13 thirds, and that would be it. This one's pretty similar. This 1/10 base, we can rewrite 1/10 as 10 to the negative 1, and then x minus 4 equals 10 to the 5x minus 8. So then that means, again, the exponents have to be equal to each other. Distributing as I rewrite it, negative x plus 4 equals 5x minus 8. Let's bring this x over to that side, so it's positive. Bring that 8 over to that side, and it looks like x is going to equal 2. Next up, we're going to have the ones where that doesn't work. So it's all great when you can rewrite it with a common base, and then you get to 5. What power do I raise 5 to get 20? And the answer is going to be somewhere between 1 and 2, because 5 to the first would be 5, 5 to the second would be 25, but I can't do anything clever with that 20. So 2 ways to solve this. One would be using the base formula from the previous section. If I rewrite this as log base 5, basically rewriting in log form, log base 5 of 20 equals x. If your calculator has the little box where you can enter the 5, great, just plug that in. If not, we would have log base 20 of log base 5. So that was that change of base formula that we saw at the end of the last section. That would equal x. And if you threw that in the calculator, what would I get? 1.8614 to 4 decimal places. The other way to solve this, which is what I'm going to end up doing on most of these, change of base isn't bad when they're pretty simple, but when it gets a little more involved, I prefer to log both sides, which I'll show in this next round. So if I have 5 raised to the x equals 20, the same way that we can square both sides of an equation, add or subtract on both sides, all kinds of operations, we can also take the log of both sides of an equation. And when I do that, it allows me to use property 3 from a couple sections ago where I can bring that x down front. And I have log 5 equals log 20. Dividing the log 5 over because it's just a number. And you can see I get x equals log 20 over log 5, which is exactly what I got using change base formula. So kind of 2 roads that lead to the same place. Again, I'm mostly going to use this one throughout the rest of these examples, but there are a couple of different ways to get there. So for this next one, let me rewrite that a little bigger down here. We have a base e. So anytime we see base e, we want to put natural log with that because it's going to make the simplifying a little bit easier. So I will natural log both sides. I can also use change of base with e if I preferred. Bringing the 7x down front leaves ln e equals ln 13. And there's the reason to use natural log with this is natural log of e equals 1. So this piece just drops out. We have 7 equals ln 13. So it just makes it a little bit easier to put in the calculator in a second. So ln of 13 over 7, dividing the 7 on both sides. And if you successfully get that in the calculator, let me see what I got. X equaled 0.3664 is what I got on that one. This next one's the same thing, just a little more to it. So again, I'll write it bigger. I can't write 9 and 2 at the common base, so nothing sneaky to be done. So I will log both sides of the equation. So here I'll bring down the 3x minus 1, and that's times log 9 equals log 2. I would divide the log 9 over next. From there, for me, I would stop writing and I would grab out the calculator because we're supposed to give this to 4 decimals. And so I would just go log 2 divided by log 9 in the calculator and hit equals. And then the next thing I would do would be to add 1 to it because we would add the 1 over. So just sort of thinking of our order of operations. And then after that, we would divide that result by 3, which writing it that way on paper isn't great because it would be a complex fraction as a fraction of a fraction. So the way we'd probably write the answer if we were doing the exact one would be to say x equals, multiply both sides of this by 1/3 to clear that 3, so we don't get a fraction in the fraction. And you get all of this mess, which to me isn't super helpful in terms of getting into the calculator. So from here, just do log 2 divided by log 1, hit equals, and then add 1, so plus 1, equals again, divide by 3, equals. So you're adding the 1 and then dividing the 3 and letting the calculator do all the work of kind of keeping track of all that. So if you successfully get that into the calculator, and I do recommend doing that there, 0.4385 is what you should get. And this next one, so just a little bit of simplifying to do before we get at that e to the x. So we have 6e to the x, it's minus 7, so I would want to add 7 to both sides. So plus 7, and we get 18. Divide out the 6. And we get e to the x equals 3. So now that we have that as simplified as possible, now I'll log both sides. So take a natural log here, natural log there, sneak up there with it. So x times ln e equals ln 3. ln e is just 1 again, so x equals a natural log of 3, which is 1.0986 to 4 decimal places. So next up is log equations, and we also have a one-to-one or like basis property for logs, which this first example actually pretty much shows. If I have log of this thing equals log of that thing, the only way those can be equal is if those arguments are equal. So kind of our goal here is going to be to, if we have multiple logs, and this is the way that we spot when we can use this is when we have an equation where every term has a log. We'll see some in a second where that's not the case. But we want to write it as a single log equals a single log, and then that lets us equate the arguments and then kind of solve the results. With log equations, we have to be a little bit careful. We can do everything right and pick up what's called an extraneous solution. Remember, our domain for logs, if we're thinking of the graph, is we can't put things into a log that are less than or equal to 0. So we got to be aware of 0 or negative numbers coming out when we solve. And when we rewrite these things as single logs, it's going to catch all of the real solutions, but it does introduce the possibility of picking up a fake solution or an extraneous solution. Okay, so what would this look like? This one's already set up, so it's just x minus 6 has to be equal to 5x minus 9, so I'm looking for the x that would make that true. I'll subtract the x over to this side, 4x, I'll add the 9 over to this side, and that would be 3. Dividing both sides by 4, I get 3/4 equals x. For this one, since it has that plus right there, let's rewrite that as, because it has to be log equals log, so basically like log a equals log b, that's what we're shooting for, so we can have a equal to b. So this will be x plus 5 equals log, and then 5x. So x plus 5 has to equal 5x. Subtracting the x over, we get 5 equals 4x, and divide the 4, and 5/4 would equal x. This one's going to be a little more involved. Yep, comes up quadratic. So far they've come up to be linear, which are a little easier to solve. This one's going to end up with a squared term in it. So rewriting that addition to get it to natural log of something equals natural log of something, we'd have ln of, I'm going to write the x out front just because it looks better to me rather than on the end. So then we have x times x plus 5 equals x plus 45. I'll distribute this as I'm rewriting it. So x squared plus 5x equals x plus 45. So with linear equations, remember we want to get x's to one side, numbers to the other. With quadratics, we want to get everything over on one side and then hopefully factor and solve. So x squared, subtracting the x over, we'd have plus 4x right there. Subtracting the 45 over, we get minus 45. That would equal 0. These should factor. If it's not factoring, something's gone wrong. So check your work if it doesn't factor. In real life, it doesn't have to, but in this course, I picked all examples that do factor, so you shouldn't need to bust out the quadratic formula for these. I think there's one that might come up to a root, but it's not. You don't need the quadratic formula. So multiplies to negative 45 and adds to 4 would be x plus 9 and x minus, 5, not 4. And then that adds to be positive 4, multiplies to be negative 45. So I get potential solutions of x equals negative 9 and x equals 5. As soon as you see a negative pop up, be suspicious, because you can't take the log of a negative number, so that's one of those extraneous solutions I was talking about. Multiplying these two things together picked up the real answer, but it also picked up an extra answer that doesn't check. Number 12, this one's a minus, so we would rewrite that as log base 3 of x over x plus 3 equals log base 3 of x minus 2. And now I can set x plus over x plus 3 to x minus 2. Fractions, so let's clear the fractions. We can get everything up in one line. So I'll multiply both sides by x plus 3. Those would cancel. I have x equals x squared, foiling here, and then plus 3x minus 2x minus 6. So that would be x equals x squared. That would be plus x minus 6. Notice when I go to subtract that x over, it drops out. They cancel. I'll sneak up here with it. So it would have 0 equals x squared. And so I'm going minus x. And I'm left with just a minus 6 there. So let's bring the 6 over to this side. And then I can solve that, since it's a squared, I can solve that by taking a square root. So square root of 6 equals x. Normally when we take a square root, we would have a plus or minus there. But again, because we're looking for the solution to a log equation, the negative root doesn't make sense because it's not in the domain of the function. And then the last thing we have is solving log equations, and these are going to be where there's a mix of logs and a number instead of these ones we just did were all logs. So when we have this situation, we want to get it written as a single log, so kind of like this one is already, and then we're going to rewrite it in exponential form. B to the answer equals the argument, the math inside there. And then if it's linear, x's to one side, numbers to the other as we do. Quadratic, we'll need to factor and solve. Again, checking for solutions if they happen to come up negative, because we can't put negatives into logs. Remember, logs can equal a negative, but we can't take the log of a negative number. So for this one, writing this into exponential equation, which is our first step, and on exams, it's where people get stuck. They kind of forget how to get out of this log form, and that's the place where they either make something up to get it out of log form or just kind of get stuck on the problem. I'll show you with a later example of what I mean by that. But that's the spot to pay a little extra attention to when you're studying. So 2 raised to the 5th makes the stuff inside. So 2 raised to the 5th equals 7x plus 3. From there we can move that out of the way. 2 to the 5th would be 32 equals 7x plus 3. It's a linear equation, so we just get everything away from the x. So subtracting 3 over, and we get 29 equals 7x, and then divide both sides by 7. 29 sevenths equals x. I think the computer will take 29 sevenths or that rounded to 4 decimals. I would just put in the exact fraction if that's available. That's what that one would look like. For this one, we'd have 4 raised to the negative 7 equals x to the 9th. When we were solving, I'm going to rewrite that the other way just because I prefer to. When we're solving a power, if this had been x squared, we would take the square root. Since it's x to the 9th, we're going to take the 9th root of both sides. And the 9th root of x to the 9th would make x, and then if you do 4 raised to the negative 7 and take the 9th root of that. If all goes well, let's see, I got 0.3402. So these next couple are a step back from where we just were. We have to do a little bit of math to get this written as log of a single number. So for this one, we'd have log base 3 of x plus 3 over, because it's minus, x minus 1 equals 1. And then right here on exams is where people get stuck. They get this piece okay, and then they'll just kind of drop the log off and pretend that x plus 3 over x plus 1 equals 1 or something. It doesn't. We got to do the base to the answer equals the argument. Again, most common error for this style question. So 3 to the first equals x plus 3 over x minus 1. We will clear that fraction by multiplying both sides by x minus 1. So on this side, that would be 3x minus 3 equals x plus 3. Subtracting the x over, we'd have 2x. Adding this 3 over, we would get 6. Dividing both sides by 2, x equals 3. Looking back at the original equation, 3 plus 3 is 6, so it keeps this one positive. 3 minus 1 is 3, so it keeps that one positive. So that's a legitimate solution. Last one, so we have log base 4 of x times x plus 6 equals 2. So 4 raised to the second equals this. And I'll go ahead and FOIL that out while I'm here, or distribute. And then this would be 16, and since it's quadratic, I need to get it to 0, so I'm going to write 0 equals x squared plus 6x, and then that would be a minus 16 on that side. And as I was saying, these should factor. If yours isn't factoring, you probably just did x plus 6 equals 2. Again, I see that far too much, so make sure you get the base in there. X plus 8, x minus 2, multiplies to 16, adds to be 6. So potential solutions of x equals negative 8, that does not check because I can't take the log of a negative, and x equals 2.